So as a first application, I'm going to show you the inequality proved by Cauchy and Davenport independently. But I will also show you the proof without using combinatorial Lewis-Lenses. Okay. Right. So let's say you have gamma that's group, and A be a subset of gamma. Then, and okay, it's an abelian group. And for A plus B, so we are using plus the sum, the addition as an operation for this abelian group. And A plus B is sum of the all pairs of elements in A and B. And then this is a theorem due to Cauchy-Davenport. So Cauchy proved it in 1813 and Davenport proved it in 1935, which says the following. So let P be a prime and A be the subset of GP, right? So 0, 1 up to P minus 1. Then the question is, how big is the A plus B? And the theorem is that it's, of course, your set cannot be bigger than the P, right? Because A plus B is a subset of GP. GP has size P, so you can never be bigger than P. So that's why I put P here. And in another case, it's going to be the size of A plus size of B minus 1. Now, let me first give you an idea why this is tight. Right? So for instance, let's say A is 0, 1 up to A minus 1 and B is 0, 1 up to B minus 1. Then what is A plus B? A plus B is going to be 0, 1 up to A plus B minus 2, right? Assuming that P is big enough, right? If P is big enough, you have this. So that means A plus B, the cardinality of A plus B is equal to A plus B minus 1, right? Yeah, this has size A, size B, this is size A plus B minus 1. So this means that if this theorem is true, then it's tight. Now, I'm going to show you a proof not using combinatorial stanza. So this is a proof by induction. Induction on the minimum size of A and B. So by symmetry, we may assume size of A is less than equal to size of B, right? And also, size of A is at least 2, because if A has only one element, then it's trivial. If A has only one element, then A plus B has same size with B. It's only shifting. And we can also assume A intersection B is empty, or A intersection B is A. Why? The reason is, otherwise, let's say A prime be the intersection and B prime be the union. Okay, then what's happening is A prime plus B prime is a subset of A plus B. right? Because whenever you choose an element in A prime and element in B prime, then the element in B prime is either from A or B. If it's from A, then you can think of the element from A prime from B, or the other way around, right? So any element in A plus B, A prime plus B prime, is an element in A plus B. And note that in terms of cardinality, A prime plus B prime is equal to A plus B. So if we have a lower bound on the size of A prime plus B prime, then we have a lower bound on the size of A plus B, and the lower bound is going to be same. So we can apply induction. I mean, not induction, but if you have this, then we replace that, and then what do we have? I mean, that means A prime, the A intersection B has smaller size than A, unless this is happening, right? So we win by induction. And A prime is definitely smaller than A, so this is true. If this is not true, so this means that if A prime is strictly less than B prime, then the conclusion follows. So we may assume, oh no, not A prime A. So we assume A prime is equal to A, so which means that A intersection B is A. Right, so empty. Yeah, we need to say that both A, B are non-empty. Right, I forgot to say that. A, B are non-empty. All right, so that's why I can always assume that A intersection B is empty, or B contains A. Now, what can you do? If we multiply a non-zero element to both A and B, right? So like QA, A prime is QA and B prime is QB, right? Then A prime plus B prime is the same. Right? Nothing changes. Right? So by multiplying, so it's the same problem. Thus, by multiplying A minus B inverse for some AB in A, we may assume A contains two consecutive elements, right? Let's say A and A plus 1. Now, and then by adding minus A to all of A, we may assume A 0 and 0, 1 are in A. What does that mean? That means I can add same number to everybody in A and everything is same, right? the cardinality of A is same, cardinality of B is same, cardinality of A plus B is same, so it doesn't change the problem, so I might as well do it. And then that means that A contains 0 and 1. And since B is not everything, why? If B is everything, then A plus B contains everything, and the inequality is trivially true. Otherwise, trivial. So there exists B in B such that B plus 1 is not in B. And by adding minus B to all elements of B, we may assume 0 is in B and 1 is not in B. Right? We add the same elements to everybody in B and nothing changes. So we can assume that B is 0, right? Now, what does that mean? That means A intersection B is not A. Right? A intersection B contains 0. It doesn't contain 1. It's not empty. So this is contradiction. Right? Contradiction to the assumption that A intersection B is empty or equal to A. All right, so that's the proof, purely combinatorial proof. Now I'm going to show you the second proof using the combinatorial Nuestranjas. So the result is trivial. If A plus B is bigger than P. Why? Because if A plus B is bigger than P, then A and G minus B. So for every G in GP, these two have a common element. So that means that I have A equal G minus B, which means that A plus B is equal to G. This is by Pearson's principle because this plus number of that is P plus 1 or more, and you only have a P distinct values in GP, so there must be a common element. So we may assume A plus B is less than or equal to P. And suppose A plus B is less than or equal to A plus B minus 2. Right. So let C be the subset of GP such that I cover A plus B and size of C is equal to A plus B minus 2. And now we're going to define a polynomial as a product of x plus y minus c, where c is in the set C. Okay, now what is the property? So let L1, okay, D1 is size of A minus 1 and D2 be the size of B minus 1. Now let's look at the coefficients of x to the d1, y to the d2. The coefficients of x to the d1 and y to the d2 is what? So d1 plus d2 is a plus b minus 2. And we are multiplying a plus b minus 2 the polynomials of degree 1. So you never use, we can never use minus c term. We're only using x and y, right? So the number of ways you choose this is going to be like d1 plus d2, choose d1, right? How many times you multiply x. And note that d1 plus d2 is less than p. Right? Because a plus b is at most p, so a plus b minus 2 is at most p minus 1. So that means this will never be a 0 modulo p. Right? Because you're multiplying, I mean, it's something, choose something, so you're multiplying. So d1 plus d2 factorial divided by d1 factorial, d2 factorial, but d1 plus d2 factorial doesn't have any p, and when you divide, you multiply the multiplicative inverse. So that means the coefficient is non-zero. So by the combinatorial Nostranza, there exists A in A and B in B such that fa plus b is non-zero. So what does that mean? That means a plus b is not in C. So a plus b is not a subset of C. Contradiction. Okay. Now, one advantage of this proof is that you can actually easily generalize. I mean, I don't know, maybe one can generalize the induction proof, but here you can generalize to this corollary. So if A1, A2, AT are the subsets of GP, then the size of their sum is at least the minimum of P and the sum of AI minus T minus 1. And the proof is the same. You basically do the same argument, but not just with the two variables x and y, you do it with the t variables and apply the combinatorial Nostranza and you get the same thing. All right. So that's our first applications.